Okay, we're going to look at a function, and we're going to actually look at a limit, but I started this time with the graph. So I've graphed the function I just highlighted over here. Z equals 5xy divided by the quantity x squared plus y squared. And I wanted to start with a graph on this one because you can see from this graph that this function has got some kind of strange behavior. From looking at the equation, you can see that when I have x squared plus y squared on the denominator of the function, that causes a problem with the domain. So domain of this function is everything except 0, 0. That would be the only point that would make this function undefined. And so that is the place we would maybe want to consider a limit as xy approaches 0, 0 to see what's happening with the function as we get close to that hole in the domain. And so this function graph looks very strange. You can see there's this part up here at the top where I'm pointing right now, and then there's some part down here at the bottom, and then here, and we've got these kind of very steep and strange looking changes in what's going on in the function. So we're going to go look at the limit and then kind of explore and understand what we're looking at here on the graph. Okay, so here we have the function that we just looked at the graph of, f of xy equals 5xy over the quantity x squared plus y squared. And even if we weren't told to find a limit as xy approaches 0, 0, because that's the only point that's not in the domain of this function, that's the place where you would want to consider a limit. All right, so we're going to go ahead and think about this limit. We did a previous example where we had a function like this, and we talked about how polar coordinates was helpful in that particular example because we were approaching the origin, and also because we got some nice simplification with the x squared plus y squared. So we have those same two features here again, so we're going to try converting to polar coordinates. When I do that, instead of having two variables approaching 0, remember that we're really just going to have r approaching 0, and theta can be anything. So if I think about all of r2 except the origin, no matter what path of approach I take to the origin, the r is approaching 0, and theta can be anything, so we can have many different paths of approach there. So we're just letting r approach 0. I need to convert all of these functions to polar coordinates. So for x, I'll substitute r cosine theta. And for y, we'll have r sine theta. And then remember, x squared plus y squared is r squared. Okay, so in the last function that we looked at sort of like this, we were able to do some nice simplification and then able to think about what was happening with that limit. So here, you might be able to see this simplification in slightly less steps than I'm going to write out. But if I simplify this, I get 5r squared cosine theta times sine theta all over r squared. And then my r squareds cancel. So when I do that, I've now changed the domain of the function. It's no longer the same function that we were working with at the beginning, but the function will have the same limit as r approaches 0. Okay, so you might notice that in the previous example we did when we converted to polar coordinates, we had some cosine and sine functions left, which we talked about being bounded. But we also had r left, and that r was approaching 0. Here, you might notice that there's no r left here. R is approaching 0, but this is what we have left. So actually, as r approaches 0, no matter what r is, this is what I get. Now the question is, what does that tell us about what's happening with the limit? Okay, so let's think about this a little bit. When theta is lots of different values, we want to think about whether we get the same answer here or whether perhaps we might get different answers when theta is a little bit different. So just kind of thinking back to your graph and thinking about polar coordinates and theta values, a couple of easy theta values to sort of think about would be the quadrant angles, 0, pi, pi over 2, etc. And if you think about that, you might notice that when you have different theta values, sometimes you're going to get the same limit, but other times you're going to get very different limits here. So for example, when theta is, say, 0, we're going to get 5 times cosine 0 times 0, not theta, times sine 0. Cosine 0 is 1, sine 0 is 0, so we get 5 times 1 times 0, and we get 0. So as we come in here along this path, if we look at that 3D graph, we should see z values that are getting close to 0. But you might remember from looking at the 3D graph, we'll go back over to that in a little bit, that there were some ridges where the z values appeared to not be approaching 0. And in fact, there are many other theta values that when I plug them in here, you should be able to think about lots of different theta values that you can plug in here that will make this expression not be 0. So for example, when theta is pi over 4, we get 5 times cosine pi over 4 times sine pi over 4. So we'll get 5 times square root of 2 over 2, or maybe 1 over square root of 2 if you want to write it that way, times 1 over square root of 2. And so we'll get 5/2, which is not the same as 0. So just like in Calculus 1, when you get different limits, when you approach the point you're approaching from different directions, in Calculus 1 you really are just checking approaching from the left and approaching from the right. If you get different limits, then you would say that the overall limit does not exist. Here, I have really infinitely many directions to approach, and in order for the limit to actually exist, I need to have that same value as I approach along all different paths of approach. So here I've found 2 paths where I get different values along different paths of approach. So just like in Calculus 1, when you get a situation like that, you would say that the original limit here does not exist. And so there are different ways to show that that limit does not exist. What I've done here is I used polar coordinates and then found 2 theta values that indicated for that polar coordinates I get different answers. We'll look at some others where we use some other strategy that may or may not involve polar coordinates. But the key here is showing that this expression takes on different values when you have different values of theta. Sometimes I have students that want to stop here and just say this is different for different values of theta. But you should be able to think about all kinds of expressions that are not really different just because it has a theta. So for example, if you had an expression, if you got down here to the end and you had cosine squared theta plus sine squared theta, that's actually the same for all values of theta. So just because it has theta in it doesn't mean that it's always going to be different for different values of theta. You really should do this step here of showing that you get different limits along different paths of approach, and then that would show that your overall limit does not exist. Let's go back and look at the computer and look a little bit at that graph. And so if I look on this graph here, if you notice, I've got my x-axis and my y-axis, and so the pi over 4 angle would be where we're coming in, where if I'm thinking about the inputs, so in the xy plane, at a 45-degree angle between the x and y axes. So that's up here. The z values along there are approaching 5/2. So you can see there it's a little bit bigger than 2. So that's where we're approaching 5/2. When we come in along theta equals 0, that would be here where those z values are approaching 0. You can see that there are some other places down here. That would be when theta is negative pi over 4 or 3 pi over 4 maybe, depending on which side you wanted to use there. You can see that those z values appear to be approaching some negative value. It would be negative 5/2 if you plug in theta equals 3 pi over 4 into your equation. But the basic idea here is you can see that those z values are approaching different outputs. They are not equal to those values, but approaching different outputs as the input gets closer and closer to 0, 0, depending on where that input is. So if your input's getting closer to 0, 0, and in this first quadrant you're going to get positive outputs, but all kinds of different positive outputs or negative outputs here. But the key is that those z values are approaching different values along different paths of approach. So we would say that this limit does not exist. We'll look at some more examples of that in some more later videos.